The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
And our next speaker is Matthew Gombeda from Lehigh University. He's a PhD candidate there. And he's been involved with ACI Committee 370 and also PCI, Blast Resistant Committee. So he's done a lot of, he's had a lot of involvement in both testing and analytical aspects.
All right, thank you, Thomas. So, like you said, I'm Matt. I'm from Lehigh. I worked on this presentation, or the material in this presentation, with two of my colleagues and advisors at Lehigh, Clay and Spencer. And what we're going to present here today is sort of in line with what Marlon just presented. It's a little bit more on the computational end. It incorporates some different methodologies to assess insulated wall panels as well. And we hope that we're able to capture more realistically what happens in these panels and create a better sort of recommended blast design methodology based on that. So just to go through the overview, first we'll talk about some of the work that we've done previously for solid wall panels and blast design, how we've sort of looked at different response criteria and different behavior mechanisms there. Also a method that we did on insulated wall panels that looks at the performance of the panels as a function of what the properties of the shear ties are. And then we're going to sort of we came up with this unified methodology that we call it. And it's more or less a synthesis of these two different methods, and you'll see how these kind of come together later on. And then we're going to take the results from this synthesized methodology and compare it to some of the conventional methods like SBEDs and things like that, and also some upcoming work that we have to build on this going forward. So I mentioned that this was sort of a mashup, if you will, a synthesis of the two approaches. And I'm not trying to do a shameless plug here, but we have these two papers that we've published already that are essentially the two different methods. The one on the left is our performance-based approach for solid wall panels. How do we look at component-specific response criteria? I'll get into that in a little bit. And the one on the right is how do we actually take known shear type properties, known wall panel geometries, and come up with a partially composite resistance function for these components. So we're essentially slamming these two methods together. So the first thing that I want to go over is the background of the stuff that we did on the solid panels. So if you imagine this pretty simple Venn diagram here, there's like two extrema that I like to call it for blast resistant design of solid wall panels. You can do something very simple like SBEDs and say that you have these idealized material properties, you have very simplified definitions of how you're to assign all these resistance criteria in the modeling approach. And then you can go to something a lot more complicated, right? You can go to like LS Dyna, for example. That's very high fidelity. You have many, many degrees of freedom. You have spreads of damage, things like that. And that has a high computational cost. It may be more realistic, but what we've tried to do is find the balance between the two. I'm a firm believer that everything has a balance, including this. So this solution, sort of imagine it as that bar shifting between the two extrema on the bottom. You can sort of move that bar left and right to get a balance between these two methods. The thing that we're doing right here is sort of in the middle, and I'll explain in detail a little bit more about how that works. But the key thing that I want you to take from this is that we're sort of balancing between what's really complicated and what's really simple. So, I think Marlon had shown something very similar to this. This is the current antiterrorism standards in PDC. We're going to focus on the wall panels in this, so we don't have any shear reinforcing, and we're neglecting tension membranes. So the 1, 2, 5, and 10 is sort of the conventional. If I talk about conventional response limits, that's what I'll be referring to. The issue that sort of motivated this whole thing is that we can have wall panels that have totally different designs with more or less reinforcement and geometric properties, and the thing is that they reach limit states at different times, different deformation levels, different strengths, all those sort of things. And because a lot of the current response criteria are based on deformations and support rotations, things like that, it kind of doesn't provide a direct correlation between what you expect to see in the panel and what the PDC tells you to do. So it's kind of similar to what Marlon said about incorporating the omega index, and we've sought to incorporate some similar things like that. So the example that I always show is that you can have two panels that have different reinforcement ratios that have, similar nominal moment capacities, for example. These aren't necessarily realistic designs, but this is sort of an exercise just to prove the point here. And you get resistance functions that are reasonably similar in strength, but the big thing here to take home is the deformations. If we're looking at peak deformation, we're looking at yield. Yield in this case is kind of similar, but you can see that, along the sort of resistance function of the component, we're seeing that it reaches limit states at different times. So the 2, 5, and 10 aren't necessarily consistent in either case with the designs. So what we've proposed in this method is a backbone curve that, this requires a little bit of computational modeling. It's a little bit more complicated than just using S-beds, but what you can do in a sense is make a simplified model using the computational approach, and you could extract the component-specific response criteria for a given panel. And we've, in a sense, here looked at yield, peak, and two other response limits in between. And this is meant to be compatible with current SDOF things. Like, we're not doing anything outrageous here. We're still doing support rotation, ductility, that kind of thing. But at the same time, we're trying to, like I said, use realistic, more compatible definitions of what the exact panel sees as opposed to just prescribing something. And the damage definitions themselves are also sort of a little bit influenced by ASE 41. We've looked at seismic components and said, like, okay, well, what are the criteria that they have there? What damage is associated with that? And we've tried to keep that in mind while we develop these things. The other big thing here that we've touched on is those of you that do single degree of freedom stuff are aware of KLM or shape function type analyses, things like that. For simply supported wall panels right now, it's pretty standard, 0.78 elastic and 0.66 plastic, but we looked at it and said, okay, because we're developing sort of the performance-based resistance function, how can we look at how KLM also varies? KLM is going to change when you crack, KLM will change after yield, things like that. And again, we've incorporated into the model sort of a way to take a little bit more complicated component-based model and transform it back to being compatible with SDOF. And that's, in a sense, what this KLM allows us to do, is incorporate that spread of plasticity, spread of damage, and it remains sort of consistent within the mechanics of the approach. And this is what it looks like. I mean, so you can kind of see here that, we did this based on a static analysis, and we showed that, yeah, 0.78 is kind of close at the beginning, but in reality, you never get that V shape, that the definition for 0.66. It starts to trend more towards like 0.7, 0.72, things like that. So it's just a more, realistic KLM in that sense. And like I said, a computational modeling framework was used here. It doesn't have to be, this is OpenSeas that we've done, it doesn't have to be. If you wanted to be more sort of design-centric, you can use SAP 2000. And there's other work that has shown that also works in this kind of regard to modeling shear transfer in structures and things like that. And if you're interested more, you can talk to me afterwards, and I can give you a little bit more details on the paper, or I can send you a copy or something like that. Unfortunately, I don't have enough time to go through all the details of this. And the important thing here is you can actually use expected material properties as well. So because this is a performance-based approach, and we want to incorporate what the panel will actually behave like, these sort of things are essential. Now, you don't necessarily have to do the actual pulled stress strain curves for rebar and things like that. It's certainly okay to some extent to do like a bilinear curve where you go yield and ultimate and apply the dynamic increase factors accordingly. We've done some work with that as well. So there's some flexibility involved here at the hands of the engineer. And essentially, I won't spend too much time on this, but it changes the equation of motion a little bit. Now we have KLM as a function of the deformation at a given time. We neglect damping in this case, common for blast-resistant design. And then we have the resistance function as well as a function of Y of T. So it's a nonlinear approach, but I think, you'll see an example later. It's not as complicated as it may seem initially. And there's the blast load at the end. So sort of crucial to this is looking at the static test as well. So we've used comparisons with static test data just to make sure that our approach captures the relevant limit states of the panel. And again, this is baked into the paper, but I just wanted to show this to reassure that, you know, we've gone through the steps to evaluate that the model works statically before we jump into a dynamic effort. And this is one of the last slides here before I go to the insulated. We did 13 panels using this approach, and we compared what the actual peak deformation was from the blast test, what you would get in S-beds, and what you would get using our approach. And we've also compared the damage levels as well. So what you see, our approach matches the visual prescriptive damage in all the cases based on those definitions that I defined a little bit earlier. It's not always the case for S-beds. It's a little off because some of the assumptions that are made. So the point that I always want to make is that, you know, it's okay sometimes to use a little bit more of a performance-based approach where, you know, in the end, it's a little bit more complicated. It's not too complicated, but we've matched all of the damage that was visually written down after the. So now I'll go into the insulated wall panels. So just as an example, insulated wall panel, it's pretty straightforward. The important thing here is that there's break, right? There's foam insulation, and we need shear ties to tie the structure together. And there's a bunch of different shear ties, right? There's many different manufacturers, with many different stiffnesses, different design requirements, things like that. So what this means is that, sort of like what Marlon was hitting on, is that you can get a totally different panel, expected panel response depending on the properties of the shear tie. You know, ductile, brittle, distributed, discrete shear ties, things like that. They all matter. And in, you know, a design practice where you say, oh yeah, we're going to assume it's fully composite. Well, if you have a very ductile shear tie that's not as stiff, potentially, you may not get the full composite behavior in the section. So this is sort of another analytical approach that we did to say, okay, we have the shear tie properties, let's figure out what the panel actually does. So one of the things that I like to show this slide because it sort of builds on the computational approach that we use for the solids. But now we have these springs in there, and one of the studies that we did prematurely was to show that, you know, we can change the stiffness of those springs and ramp up that stiffness K that I have there, and it actually shows that, you know, as K approaches infinity, you approach a full composite response. K approaches 0, you get a full non-composite response, and, you know, realistically, you're going to be somewhere in between. So this is sort of the bounds of the operation. This is showing that, you know, indeed the panel's mechanics are heavily influenced by K, even in a simplified model like this. So we also did some static comparisons with the insulated wall panels. You know, we had the shear tie behavior properties of all the shear ties in these panels, and we looked at the model to analyze both the strength along the load history and the slip, which is these curves here, and you can see that they reasonably well match the static insulated test that we did on these panels. And there's 6 cases here. So we built upon that, and we smashed the two methods together for this presentation. So we have a way to get performance-based limit states for a wall panel. We have a way to analyze it to be partially composite. So if we bring these two together, what does that mean for blast design of insulated wall panels? So depending on what tie properties we have, we can get different response, right? So this is sort of the first step in mashing these together. It sort of shows where the limit states are at. The first panel over there is 4 very stiff connectors just at the end, versus the second one that is uniform spacing, versus the third, which has not as big or stiff connectors, but they're sort of more concentrated towards the end. And the important thing here is that all the panels reach a similar capacity, but the midspan deflections that they're happening at are different. So in a sense, this is to prove that the response limits are heavily influenced by the ties. And it doesn't have to be only the properties of the ties. You know, Marlon had talked about ductile and brittle, but it's also the placement of the ties. Because in reality, the slip is larger towards the end just based on curvature and how the panel behaves. So there's that to consider as well, which is why the model incorporates both of these. So just a rough flow chart of what I call the unified methodology. And it's just, I'm not going to go through all this. There's a conventional approach on the left side, and then there's what we're calling unified approach on the right. You can see everything on the left is pretty standard as to what you do now. You have full composite behavior you can calculate. Yield is based on average moment inertia at cracking and gross. And then you run through, you have prescriptive response limits and the prescriptive KLMs, and you do an SDOF. On the other side now, we can replace the resistance function with the simplified approximations with the one that we get from our model, the partially composite. We can extract the limit states using the first part of the method that we had before. We can extract KLM, and then we can do a similar generalized SDOF using now these new input parameters to get the dynamic response of the panel. Okay. So we did a quick case study here, looking at what the implications of this are for some of the panels that we looked at for the insulated method. So there's 4 of them that I picked here from previous tests. Normally you would do 100% composite. You could, in this case, we're going to treat the performance-based approach as a design method. So I use sort of design-oriented material properties like bilinear curve with the dynamic increase factors incorporated. The purpose of this case study is just to show sort of how SBEDS approximates things versus what our method does when we have verifications on both static and insulated, or static response limits and insulated behavior to put in. So what you can see is that there's very different response between the panels. We have panels that are a little bit stronger. Certain ones, the peak response, which is one of our criteria, is varied between 2 and 5th one there. So I mean, it's kind of all over the place to some extent. KLMs are a little varied as well. So this just kind of shows what, again, the input would be into the SDOF when we get to that stage. So to do that, I did a very simple single degree of freedom analysis for both approaches. And there's 2 different blast loads here. There's a 1089 and there's a 2170. 1089 is pretty common and standard for like exterior cladding panels, non-load bearing cladding panels. The 2170 is sort of that doubled to some extent. Just to show a higher magnitude, to show if you get a larger blast load and you push the panel to those further response limits, how things start to deviate. So we wanted to look at sort of a holistic approach to see how that matters. And then sort of the results are interesting, right? So we have, for the 4 different wall panels, the CDL is component damage level, so that's essentially, superficial, moderate, heavy, hazardous, blowout, whatever. So the conventional stuff, as you can see here, is delta UFC or whatever. So we're looking at moderate damage in cases where we have sort of superficial and others. We have moderate damage in both cases for 6 for the smaller load. For the 2170, we have performance base tells us we're at blowout, whereas the SBEDS tells us we're only at heavy. So there is some inconsistencies here. There's no, unfortunately, unfortunately, we don't have a sort of comprehensive comparison with the test data at this point. We're still working on this and still under development. But the sort of moral of the story here is that when you sort of incorporate a similar SDOF approach for both methods, the results in damage levels and performance vary. In some cases, it's very conservative, which is okay to some extent because you're not in any danger. But it also may limit the efficiency of the component. And in cases where it is under conservative, it may be something to sort of think a little bit more about to ensure that the structure is safe and maintains its performance that was intended. Yeah, future work, we're going to incorporate some blast tests. We're still going to do some blast tests at Lehigh as part of another project. We're going to hopefully incorporate some of these methodologies where we have the shear type properties and all that stuff to see what affect the actual performance of the panel, how that matters, and some other things that I'll get to in a second. So that leads into future work. We're actually we started to develop dynamic increase factors for shear ties and insulation types. So sort of what Marlin had was a factor that you could scale the resistance based on what kind of connector you had. We're sort of doing it in a similar way but a different route where you would take the shear type properties and potentially scale that curve depending on what the behavior would be like in the blast load. We're going to do experimental testing to verify these new DIFs to incorporate this methodology. We're going to, we can extend this method to other types of components, whether it be multi-span or ones with openings or things like that. Anywhere that you're looking to get a little bit better idea of what's going on, some little bit more complicated structures potentially. and it's very flexible. So the summary and conclusions, we proposed this new methodology, which was in a sense a synthesis of two previous methods with performance-based design of concrete wall panels and an analysis approach to get the insulated resistance function. The limit states vary heavily based on not only the concrete properties and the steel properties, but also the layout and the constitutive properties of the shear ties themselves. And the SDOF analysis results show that we often underestimate peak displacements. We're often not consistent with what the performance-based approach says. I mean, we still need to do a little bit more work to see overall, using a bigger set of data, what the experimental factors into. But this is more from a design-oriented approach that we wanted to concentrate on. So I hope that was helpful, and I hope you guys understood everything and enjoyed that. So I'll have any questions if we still have some time. Thank you, guys.
Matt, quick question for you. What's your definition of blowout? At what point? Is that just simple spalling, or is that a big chunk of side?
From the performance-based approach that we did, and it's sort of our definition, is that once we reach the peak capacity of the component. So what we equated that to is that in the ASCE 41, a lot of the heavier damage levels specify that the component can't take more load, it accrues a lot of damage, it's no longer stable. So in a lot of the static tests that we've shown, the damage levels and stability after the peak is not sufficient to sort of let it take on much more damage. So we've, in the approach that we've developed, we've called peak the blowout.
Okay, so that's different to spalling and pieces of spalling.
Yeah, I've had questions about that in the past. I know there's some people out there that are probably saying that the blowout is a function of debris velocity, and I'm aware of that kind of stuff, but from sort of just a component-based analysis method, we've called blowout in this case based on peak capacity. We haven't really looked at debris or anything like that in this study.
Okay, because that led to my second question, the next question, which was, did you find that when it came to spalling debris, did you find that that was happening in the first wythe, and therefore any spalling would just get caught up?
Yeah, like I said, we have to do some more experimental tests, and that's definitely something that we're going to look at is, are there other things happening besides flexural damage? Is maybe behind, if the shear ties cause spalling behind, I've seen in other people's tests that behind the shear ties you see spalling, things like that. If that has any adverse effects, we'll certainly, consider that, but I think once we do the rest of the experimental tests, we'll have a better idea of if that matters or not.
Okay. And just one other quick one.
Sure.
When you precast typically uses higher strength concrete than cast in place, and with that, I believe that ups your modulus of elasticity. Did that help you at all?
Not necessarily. I mean, we didn't really look at that. These were older tests that we'd sort of taken some data from. And the concrete design strengths were pretty consistent with what's normally done in precast. I think, 6,000 to 8,000 PSI or whatever. So we haven't gotten into sort of the smaller details I think that you're getting at, but everything that we've done and the panels that we use were pretty well consistent with what they do in practice. All right, thank you guys.